In this video, I'd like to talk about the math question of the day for Sunday, August 20th, 2023. And with this problem, we have the definite integral from an x value of 0 to an x value of 4 of this rational function x divided by x squared minus 9. And questions like these are typically seen in Calculus 2 classes. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you've attempted the problem, let's start working through this. And with this type of integral, we could proceed as normal, but you might notice that we have an issue with our domain. And the domain is something that you should always check when starting problems with rational functions, which x values are not in our domain. And we can find that by just setting our denominator equal to 0. Or in other words, we can say this denominator, x squared minus 9, cannot be 0. And then we can figure out which x values cannot be included in our domain here. We add 9 to each side, and we square root each side so that we get x cannot be 3 or negative 3. But notice the issue with 3, that's in the middle of our bounds here. Since the x value of 3 is within our bounds, we have an improper integral here. We need to split this integral up into two different pieces and then take some limits. So let's split this up for the first piece with bounds from 0 to 3 of our function x over x squared minus 9 dx. And then our second piece will be from 3 to 4 of that same function. But we still can't plug in 3 since that's not in our domain. But what we can do is take some limits. So let me make a little bit of room so that we can keep working. We can take a limit, and we'll need to define some variables here. But let's say as a approaches 3 from the left-hand side, we'll be taking one-sided limits here of the integral of 0 to a now of x over x squared minus 9 dx. And we'll need another limit for this one. So we can use another letter. Let's use b. And we'll say b will approach 3 from the right-hand side of our integral from b to 4 of x over x squared minus 9 dx. And we just need to evaluate this integral here. And then we can apply the limits at the end. So let's evaluate the integral separately so that we don't have to rewrite it multiple times. Let's just say we have the definite integral of x over x squared minus 9 dx, this indefinite integral without any bounds. And with this integral, we can actually just use a simple substitution using Calculus 1 techniques. Since notice that our denominator, if we set u equal to this denominator, x squared minus 9, its derivative, multiplied by a coefficient, is in our numerator. So let's figure out what du is in terms of dx. We have du is 2x dx, but we're going to substitute for x times by dx. Let's divide each side of this by 2. We get du over 2 is x dx. And now we can make that substitution. We plug that in here. We get the integral of x dx, but that's just du over 2. We can put the 1/2 on the outside. And in our denominator, this is just u. And you might recognize that this integral is just the natural log of the absolute value of this u variable. But u is x squared minus 9. So let's back substitute there. And since this is indefinite, we would have to put plus c. Now, going back to the integral we're concerned with, we know that each of these will evaluate to this 1/2 multiplied by the natural log of the absolute value of x squared minus 9. So let's use this information and rewrite these, but we also need to rewrite these with our limits now. So we have the limit as a approaches 3 from the left-hand side, and we know this integral evaluates to this expression here. we have 1/2 multiplied by the natural log, let me rewrite that, of the absolute value of x squared minus 9. And we will be evaluating this between bounds of 0 and a. And then we'll add the limit as b approaches 3 from the right-hand side of this expression, 1/2 multiplied by the natural log of x squared minus 9. And we're evaluating this between bounds of b and 4. So let me make a bit more room here, and we can finish our problem. We just need to plug in our bounds. Now, when we plug in values of a that are slightly less than 3, and we square that, we'll get a number that is slightly less than 9. And taking a number that's slightly less than 9 and subtracting 9 from that, we will get a natural log of a number very close to 0, but on the negative side. Of course, though, we're going to take the absolute value of that, so it will become a positive number. And in the end, what we essentially get is 1/2 multiplied by the natural log of a number slightly bigger than 0. And I'll write that as the natural log of 0 plus, and we can come back to this. We can now plug in 0, and we're subtracting this lower bound. We have minus 1/2, the natural log of the absolute value of negative 9, which will just be positive 9. So we have minus 1/2, the natural log of 9. Then we add what happens when we plug in our bound of 4 here. We have 4 squared, which is 16, minus 9, which would be 7. We have 1/2, the natural log of 7 there. And then we plug in b, and we're subtracting that. We have 1/2, the natural log of b squared minus 9, but b, we're taking the limit as b approaches 3 from the right-hand side. So it's a number that is slightly bigger than 3, and we're squaring it, so it will be slightly bigger than 9, and then we subtract 9, and we'll end up with a number that is slightly bigger than 0. So we can again write this natural log of 0, but with a plus sign, since it's slightly bigger than that. But in the end, these expressions are infinite. The natural log function, you might remember, looks essentially like this. And the smaller the input, the closer the input is to 0, the bigger the output is, though it will be a negative number. So I should say, as the x value approaches 0, the output gets more and more negative. So that approaches negative infinity. So in the limit, this is negative infinity. And likewise, this would also be negative infinity, though we're subtracting a negative, which is the same as adding. But we need to be very careful here. We can't just say that negative infinity plus infinity will cancel each other out. We can't treat infinity like a number. It's more of a concept. So we need to go back and think about what we found. Essentially, this expression here, which came from our integral when we split it into these two parts, we're looking at this first part that had a negative infinity in it. What we essentially show is that this integral is divergent, and likewise, since this other integral also evaluated to having a plus infinity in it, this other integral from 3 to 4, this would be divergent as well. And frankly, in improper integrals, if we split it up and one of those parts is divergent, that just means the entire integral is divergent. Though in this case, both integrals are divergent, which technically means that you can't break it up like this. But of course, it's hard to know that ahead of time. You really prove that for yourself as you go through and end up with infinity in your answer. So this is not possible because these are each divergent. But the main idea is that this improper integral here, since we couldn't find a convergent value, we know that this is divergent. This approaches infinity. Or we can say that this integral diverges.